Now we move on to chapter 4, something new and different. We're going to talk about work and energy principles. As it turns out, many problems we've done already could also be done using work and energy principles. Sometimes just applying Newton's laws directly is easier. Sometimes work and energy is easier. So it's good for you to be capable with both approaches, and that way you can pick and choose the best approach. So we'll just introduce some of these principles today. So we'll present the basic work energy principles and then look at how they can be applied into some engineering problems, particularly those that require us to relate changes in speed to changes in position. Those are the most straightforward applications of work energy problems. So we just finished solving this problem in the last lecture. This is a sphere sitting on a hemicylinder or a cylinder. It slides over the cylinder and then at some point separates. And the question we answered before was at what point does it separate? So suppose we want to do the same problem using work and energy principles. Okay, so first we need to know how these work or what they are. So suppose we have some particle um, seen here moving along some path from point 1 to point 2. And there's some force applied to that. The force does not have to be constant. It can vary as a function of position or time or whatever. So there's some particle moving on a path due to some force F. Newton's second law says F equals ma. If we take the dot product of both sides of this with a differential or infinitesimal displacement dr, then we get F dot dr is ma dot dr. Ma dot dr can be written as m dv dt dot dr, and dr can be written as v dt. Okay, it's the same thing. So mv dot dv can be written as the differential of 1 half mv dot v. Okay, so now we can take this, substitute this in here, and then integrate both sides like this. And we're integrating along the path that the particle takes in space. So we rewrite that here. This thing over here is an exact differential, so we can pull out the 1 half m, and the differential dv dot v integrated can be written like this. So the right hand side is 1 half m v squared from point 1 to point 2, so it's 1 half mv2 squared minus 1 half mv1 squared. It'll turn out, as we'll see, that this is kinetic energy. So this right here represents the change in kinetic energy from point 1 to point 2. It doesn't say anything about how it got from point 1 to point 2. It just shows a change in kinetic energy between the 2 points. So if you know the beginning and starting points, you can calculate this so you know what this should be. All right. This is a work term. Okay. So we write U for work going from point 1 to point 2 as this integral along the path of f dot dr. Okay, so that's the work done from point 1 to point 2. This is the change of kinetic energy. So our work energy principle is that the initial sum, so the initial kinetic energy plus the work done and going from the beginning to the end equals the final kinetic energy. All right. So the kinetic energy we start with plus the work done gives the final kinetic energy. If the work done is positive, you have more energy at the end than the beginning. If the work done is negative, you have less energy at the end than at the beginning. Okay, so we can do a little more with this. If we have some force F, we can look at normal and tangential components. Okay, so U12 is F dot dr along the path, F dot vdt from T1 to T2. Okay, vdt can be written as v, the speed, times u hat. The unit vector in the t direction, the tangential direction along the path. V can be written as ds dt, and then we can right, this, you can sort of cancel the dt's, and this is ds. So we can write the work done as the integral along the path from S1 to S2 of f dotted with the tangential unit vector ds. All right. So what if the force is constant? Suppose we have some force F with an x and y component, and all of those are constant. Then we can calculate the work done and going from P1 to P2. And you can work through all the math, and it's just the force dotted with the change in the position vector, right? So if point 1 is here, we'd have some vector r1 here. Point 2 is here, we'd have some vector r2 here, and r2 minus r1 is the vector going from point 1 to point 2. Okay, so it's independent of the path, right? If the force is constant, the work done is just that force dotted with the vector from the initial point to the final point, independent of the path. So let's look at some examples. Okay, so suppose we have a jet airplane, an FA-18 Hornet, taking off from a stationary aircraft carrier with two propulsion systems, two jet engines, and a steam-powered catapult, right? So the catapult helps to launch the plane, get them up in the air right away, okay? So a fully loaded Hornet weighs 50,000 pounds, and it goes from 0 to 165 in 300 feet, while its two engines are at full power, each generating 22,000 pounds of thrust, and the catapult is engaged. Determine the work done on the aircraft during launch, the work done by the catapult, and the average force exerted on the catapult by the catapult on the aircraft. Okay, so we model the airplane as a particle. The free body diagram is here. There's a normal force, there's a force from the catapult, a force from the thrusters, and there's gravity. We don't really have to worry about these vertical forces, so we'll just worry about the horizontal. So we find the change in kinetic energy, and that'll be equal to the total work done, and then we can compute the work done by the thrusters and by the catapult, as we'll see in a minute. Okay, FC we'll call the average value of the force of the catapult. So let's look at the balance principles. So we know that T1 plus U12 is T2. T1 is 1 half mv1 squared. T2 is the initial kinetic energy. T2 is 1 half mv2 squared. One is right just as we leave the boat, the aircraft carrier, and 2 is right before takeoff. So, excuse me. So 1 is initially, 2 is right before takeoff. So the work done by the thrusters is the thruster force, the integral over the path of the thrusters dotted with the position. The path is just a straight line, horizontal. It goes from 0 to 300 feet. The force is 44,000 pounds constant. We integrate over x, and we get 1.32 times 10 to the 7th foot-pounds. The catapult, if we assume it's constant, the catapult force works the same way, and it's 300. We have 300 times FC. Okay, so that we don't know what FC is yet that we're trying to calculate. So the work done by the catapult is 300 times FC. Kinematics, we have zero initial speed, and final speed is 165 or 242 feet per second. So U12 is T2 minus T1 is 4.55 times 10 to the 7th foot-pounds. That's the total work done by the catapult and the thrusters on the airplane as it launches. The work done by the catapult then is the difference between the total and what we calculated for the thrusters. So it's the total minus what's coming from the thrusters is 3.227 times 10 to the 7th foot-pounds. And T12 is 300 FC, so FC is 108,000 pounds. It's dimensionally correct. We'll go down here. The work done on the plane is equivalent to pushing a 70-pound wooden crate over level concrete at a constant speed for 200 miles. So of course it does a much higher force in a much shorter distance to get the same work done. And the force of the catapult is more than twice provided by the engines. That's why you use the catapult, because it gives a big boost, really gets the plane going quickly, gets it up off into the air and off the boat. Second example is a pulley system. Okay, so a block of mass 20 kilograms is connected via this pulley to a winch right here. Okay, the winch exerts a constant force of 130 newtons on the cord. So there's a 130 newtons here. That tension will be transmitted to here. We'll assume no friction here, no stretching of the rope, but there is friction here. Okay, so the friction between the block. Oh, there is. We'll ignore friction there. Sorry. So if we let this height be 0.8 meters, if the block starts from rest in the position shown, determine the speed of the block when it's moved 1.15 meters, right? So we start this winch up. It provides a constant force of 130 newtons through the rope to here, but the angle changes as the slider moves this way. So um, the question is, how fast is this moving when it's traveled 1.15 meters and is directly under the pulley right here? So we model the block as a particle. The free body diagram is here. There's gravity down and normal force up, and then there's this tension from the rope, which is at an angle theta from the horizontal. We let I be the horizontal direction positive left, J be positive up. Okay, so the initial kinetic energy plus the work done is the final kinetic energy. T1 is just 1/2 the initial velocity squared. T2 is 1/2 m times the final velocity squared. The work done is U12, which is the integral from d to 0 of minus p cosine theta dx. Okay, x tangent theta is h, right? So we're relating this position here to theta, really, right? So it relates the distance here to theta using that constant height h. And so tangent theta dx plus x secant squared theta d theta equals 0. It's just differentiating this. So tangent theta dx plus h over tan theta secant squared theta d theta is 0, or dx is minus h over sine squared theta d theta. So notice we have dx here. We want to integrate. We either have to get rid of the cosine theta and make it a function of x, or we get rid of x and make it dx and make it replace it with d theta and integrate over theta. So if we do the latter, the work done is the integral from arctangent of h over d to pi over 2 of p times h cosine theta over sine squared theta d theta. We can do this integral exactly. We put it here, we put in the limits, and so we find the work done on that little block is minus p times h minus the square root of d squared plus h squared. This is always greater than h, so this is always negative, so the work done is positive. Okay, and we did use a trig identity to do that. We set the initial velocity to 0, so that is the block starts at rest, and then we turn on this force instantaneously. And so the initial kinetic energy is 0, so this work done is equal to the final kinetic energy. We can solve this for V2 and we get this expression, and we put in the numbers, we get about 2.8 meters per second. So the velocity of the block just as it passes under the pulley is 2.8 meters per second. Now you could have done that using Newton's laws, but it's much easier in this case. So anytime you're asked to do something with initial velocities and final velocities, for example, and you don't care about the middle, you should always at least consider energy methods and see if they'll help. Okay. All right. Here's another way to do this. Okay, so the block is modeled as a particle. The reactions at the pulley do no work. Okay, so there's no work done by the reactions here because there's no motion. So only P does work. Okay, so we could have looked at the work from this end rather than this end. So T1 plus U12 is T2, that we've seen before. And the work of P is P times delta, and where delta is the distance this travels. And then if you know how far this travels, you can figure out how far this will travel. So delta is L1 minus L2, okay, where the 1 and 2 are these positions here. It's a change in the initial and final length. So it's the square root of d squared plus a squared plus little l, which is this distance, minus h plus l, which is this distance. And so this is the square root of d squared plus h squared minus h. So basic idea behind this alternative approach is to find the work done by the pulley and relate that distance traveled here, the work done here, to the distance traveled here, and you can get to the same result. Okay, so again, there's more than one way to skin this problem, and either way you do that is perfectly reasonable. All right, that's enough work for now.